Hello, my name is Oliver. I am a teacher and game programmer, and I want to do a video today about vectors, which are a critical data object that game engines like Godot use to store the positions of objects, and also to handle moving those objects around. In this video, we're going to go over what is a vector, a couple ways to make vectors interact using math, and then we're going to do 3 examples of actually deploying this in a game. So here's the syntax. This is how we declare a new vector in Godot. You declare a new vector 2 and you pass in 2 components, x and a y. In 3D, this will say vector 3 instead, and it'll have a z component as well, but I'm mainly going to focus on 2D because it's easier to visualize, but it's the same math pretty much everywhere. So in this case, I have a vector 3, 5, and oftentimes that'll represent a point in space. So in math class, you remember this like coordinate plane, hopefully. If you go over 3 and up 5, this vector represents this point in space. Mathematically, we sometimes think of vectors as representing arrows rather than points. So if there was like an arrow pointing from 0, 0 to 3, 5. When we think of them as arrows versus when we think of them as points, depends on whether we're thinking of a vector as a position or as some kind of motion, because we use them to represent both. And we'll talk about that in a minute. So one of the main places you're gonna see this show up in a game engine is the position of an object. So over here, here are all the different properties of my player, and one of them is position. It has an X and a Y position. 0, 0 is the top left of our screen, and as I increase X, our character moves right. As I increase Y, they move down. You might notice here that the Y-axis is like inverted from what you might be used to in math class, right? We're used to in math class, like 0, 0 is the bottom left instead of the top left. This is because of like old computer rendering standards. We render the top left pixel of a screen first, and then we work our way down. I think it's dumb and this should be inverted, but whatever, we're stuck with it. So just keep in mind that the y-axis in our game engine is a bit backwards from how we think of it in math class, but that doesn't change any of our math or anything. So I'm gonna go on explaining it like you may have seen it in math class. We've got a vector, like our character's position. What can we do with these vectors? Well, we can add them together. So here I've got 2 vectors. Vector A is 2, 2. That's 2 over and 2 up. So I represent that with this blue arrow. Vector B is 1, 4. So that's 1 over and 4 up. I represent that with this orange arrow. And if I were to add these vectors together, you get a vector back. And that vector is pretty simple. You just add the x's together and you add the y's together. So I would end up with 2 plus 1 is 3, and 2 plus 4 is 6. So you end up with this green vector out here. And notice that this green vector is what you would get if you stuck both of these other 2 vectors together, right? Notice that if I stuck the orange and blue vectors tip to tail, I end up with the same destination as my green vector. Okay, and then if you subtract vectors, I've got the same 2 starting vectors, the blue and the orange one. And it's the same idea. You subtract the x's and then subtract the y's. So 2 minus 1 is 1, 2 minus 4 is negative 2. And what this ends up doing is it describes the vector, the path we would have to take to get from point B to point A, right? It's 1 over and 2 down to get between the 2. So this will be useful for, I'm gonna show you 2 practical examples now. So here I've got a position, right? This could be like my character's position is 2, 2, so it's 2 over and 2 up. And I want them to be able to do like an air dash, right? I'm imagining like a game like Celeste, for instance. So the air dash moves me over 1 and up 4. And all I have to do is if I add these together, I get that resultant vector of 3, 6. And if I override my position to that value, now my position is going to be up here. So I can move from here to here by adding vectors together. This is one of the most common ways you're going to do math with vectors in Godot. It's to create motion. And this is what I mean when I say we can think of them either as points or as arrows. Because while both position and the dash velocity are vector 2s, one of them describes a point in space, whereas one of them describes like a motion through space. So here's another example. So here I've got, if I'm subtracting 2 vectors, this can be used for targeting characters at each other. So if I want to find the direction between my enemy and my player, say I wanted my enemy to chase my player, right? I could say, have these 2 vectors represent the player position and the enemy position. Same vectors, 2, 2 and 1, 4. So here's the enemy, here's the player. And if I subtract the 2, I get a vector that describes the distance between them. and the direction between them. And so I can use this vector then to move my enemy towards my player. And we'll do an example like this in a bit. But this is how we'd end up making the enemy like chase our player, or if we want to do like homing missiles or something, right? This is the technique that we would use. 2 more math things, and then we're going to go do some examples. There's a trick that you can do called normalizing a vector. And in Godot, it's really simple. You just say vec_a.normalized. And if you normalize that vector, it shrinks it down to be exactly 1 long. So right now, this is maybe like 7 and a bit long, right? If I were to lay this flat, it would go out to like 7 and a bit. What's useful about this is we end up with a short vector, but it has the exact same direction as our original vector. So this orange vector can be used to describe purely the direction that original vector was pointing. You'll see why this is useful later. And we can also scale vectors by multiplying it by a number. In this case, a float. Remember, that's just like any decimal number. So I take a vector with an x and y, both 1 in this case. That's the blue arrow here. I have a scalar, right, because we're going to scale this vector up by 5 times. If I just multiply those together, I get back a vector that is just x times 5, y times 5. In this case, 5, 5. So this would let you scale up or down a vector. You know, if this number was like less than 1, if this was, say, 1/2, it would shrink the vector by a factor of a half. Okay, so that's all the math stuff we're going to go over. Now let's try actually writing some code with this. And we're going to start out simple and build up to more complex examples. All these examples are based on our game, Cappy and Tappy, where it's a platformer with a lot of obstacles and stuff. So let me just run this so you can see the basics. I've got a really basic character controller here, no animations, no flipping. I wanted to keep it really simple. And so you can run around and jump on the blocks here, and that's it. Okay, so what are some directions you might want to take a platformer like this? Well, we're going to add some hazards to this environment. So I've whipped up these little spikes here, and I want it so that if you touch them, it will kill our character and send them back to the spawn point. So right now, all the spikes do is they run this function here. So it's just going to print out, boom, character should die, character should die. Let's try declaring a variable that is going to be the position we want to send the player back to. So I'm going to declare a new var. I'm going to call it spawn point. It is a vector2. And we'll declare a new vector2 with these coordinates. Let's say 100, 100. That's 100 from the left, 100 from the top. What we're going to do is we're going to overwrite our character's position. We're going to set it equal to our spawn point. So now whenever we hit those spikes, we'll set our position to 100, 100. So this is just to get the hang of our basic syntax here. We declare a vector, and then we can overwrite vectors just like we can any other variable. So let's try that out. So when I touch this, boom, it warps me up here to the 100, 100. 100 from the left, 100 from the top. So we can adjust these numbers if we want to bring it further from that top corner. There we go. So here's going to be our spawn point, is going to be around here. So we've got a real simple like respawn system working. I'm also, while I'm here, I want to zero out our velocity so that if we hit this thing like with some motion, we don't maintain that motion into our respawn. So I'm just going to take our character's velocity and set it equal to a new vector2, and I'm just going to set it to 0, 0. So this means I'm going to have no x velocity, no y velocity. So let me run that one more time. And you can see, even if I come down really fast on this thing, I'm pretty much still when I land, and then gravity takes over and I fall. Now let's try another obstacle. I've got an arrow here, and it works the same way as the spikes. It's tagged as in the kill player group, so that when the player overlaps it, they'll die. Now, of course, an arrow like this isn't a very interesting obstacle. It's just the same as the spikes. So we're going to write a new arrow script that moves this arrow over time. So we're going to do, this is the most basic like movement script you can possibly do. Okay, so let's start by declaring a velocity variable. So I'm going to say var velocity. It is a vector2. Let's start it out like, let's imagine this arrow is going to move right. So that's a positive x value. And I don't think it's going to be moving up or down at all. So we'll just keep that at 0. This arrow needs to move a little bit every frame, and then that's how we get this kind of smooth looking motion. So I'm going to take my global position and I'm going to add on to it. So I'm going to say plus equals. I'm going to say plus equals my velocity. This is about as simple as it gets. Let's see what that does. And I don't know if you could catch that. I'll restart the scene for you. I don't know if you can see, the arrow just rips off the screen. It's moving really, really fast. And that's because every frame, which is like hundreds of times a second in a lightweight game like this, it's moving the thing 100 to the right, right? So we're taking our position and adding 100 onto the X value, adding 100 onto the X value, adding 100 onto the X value, every frame. And so it's way too fast. But so what we can do is, of course, we could just decrease this value, right? Decrease the velocity. And then we get a nice slower moving arrow. It still kills us. Good. The trouble with this is that this is now extremely frame rate dependent, right? It depends how fast our game loop is running. If our game loop is running really, really quickly, say on really nice hardware, this arrow is going to move faster. And so you don't want your game like speeding up or slowing down depending on the frame rate. A funny story, when I was playing Hotline Miami 2 for the first time, very challenging game, they did not control very well for this frame rate issue. So I would unplug my laptop, which would make it go into like efficiency mode. So the frame rate would drop and the game would run a lot slower. So you had more time to react to enemies and stuff. And that's how I beat some of the levels. I've since beaten it legit. Don't crucify me for cheating on Hotline Miami 2. But this makes it into real games, but it's really easy to fix, especially in Godot. So what we're gonna do is we're gonna scale up or down our velocity depending on our frame time. Sounds really complicated, it's really easy. All we have to do is multiply by delta. Delta is this variable right here. It's just a flat number, and it defines how long it's been since the last frame. So it'll always be a very small number because it's a fraction of a second, right? So it's a very, a lot less than 1. So it's always gonna shrink our velocity down, and it shrinks our velocity down by exactly the right amount to always compensate for our frame rate, right? If we have a crazy high frame rate, delta is gonna be very small, so we are going to move it a very small amount every frame. And if we have a very low frame rate, delta is gonna be huge, and we're gonna move the arrow more to compensate. So it'll move at the same relative speed. That's a really long explanation, but this is very useful to understand. This is gonna show up now and again, but for now you can just trust me. We're gonna scale our velocity by delta. When I run this, we should get an arrow, nice, consistently moving at 100 pixels per second. And so now we can change the speed however we want. This is why I like to declare this variable up here. You can dial this in as you go here. So if I want it to go faster, if I want it to go kind of up at an angle, I could add like a negative value here, and that'll make that a little bigger. Minus 50 and minus 100. We can see that kind of makes it go up at an angle. If I want it to go like down at an angle, I can make both these positive, right? Remember that this is positive X, positive Y. So we can make it go down. So this is about the simplest like motion program that you can do using vectors. Now we're gonna do the hardest one we're gonna do today. I've got a ghost here. And the ghost is, right now, it works just like the spikes or the arrows. If I touch the ghost, I die. But what I want the ghost to do is chase my player. He's always going to be moving after our player. So how do we create that behavior? Well, first I need a reference to the player. So I'm going to grab the player from my hierarchy over here, drag him into here. I'm going to hold control. And this is just gonna create a variable that's a reference to my player. Let's also set a move speed. And in this case, I'm actually gonna make move speed just a float, not a vector, because the actual velocity, the actual direction we need to move is gonna change every frame. This is going to be, say, 150, a bit less than my arrow. The actual motion, the line where we move this thing is gonna look just like my arrow. So I'm actually just gonna copy that right over. I'm gonna go back to my ghost, put this here. And the trouble with this, it's gonna give me an error because I don't have a velocity declared yet. So we need to calculate that velocity, right? It's not the same every frame. It needs to constantly be changing to point at our player. So let me write this out. Var velocity, it is a vector 2. And how do we calculate this thing? How do we know what direction is moving towards the player? Well, if you remember from our lesson here, if I wanted to get a vector that describes the path I need to take to get from point A to point B, I just subtract those 2 points. I do point B minus point A, and it tells me what direction I would need to take to get to the end. Okay, so let's do that. I'm gonna say var dir, right? This is a direction we need to move. This is going to be a vector 2. That's going to be equal to the player's position minus the enemy's position. So I'm just going to say player. And if I say player dot, I have access to any of the variables and stuff that define that player. So of course I have access to their position. And then I'm going to subtract the enemy's position. I can just say global position here because it knows that if I'm not specifying whose global position I'm talking about, I'm going to be talking about this object, whichever object has the script on it, which in this case is the ghost. If it helps you think about it, I sometimes do self.global position, right? Because this is the players and this is myself being the ghost in this case. I figured out what direction do I need to move to get to the enemy. For now, let's just set my velocity equal to that dir. And I'm going to show you something that kind of goes wrong here. Okay. So maybe you can see the ghost is chasing me, but as he gets closer, he slows down. And as he gets further away, he speeds up. And he still kills me. So this could be a mechanic that you're interested in doing, that he speeds up as he's further away, whatever. But generally, this is not a desired behavior. And the problem here is that this dir vector, remember, this describes the full path that I needed to take to get from the enemy to the player. And so that path will be longer if we're further apart, and it'll be shorter if we're closer together, which means my velocity is going to change wildly depending on how far away I am. So I want this dir to always be the same length. I don't want it to be changing every time, but I do need its direction. I do need it to be pointing at my player. And well, we just learned a tool for this, right? Normalizing. I can take any vector and squash it down to always be one long. So this is pretty simple. I'm just going to say dir equals dir dot normalized. And that's going to shrink this vector to always be one long and then overwrite itself. So it deletes the old data and just keeps its direction. Because all I want from this is really what direction do I need to chase the player. All right, if I run this, I'm going to be a bit slow. I don't know if you can even see that he's moving. He's moving 1 pixel per second because I just changed the dir to always be 1. So that works, but it's pretty slow. So we can just scale this up, right? We can take any vector and scale it by just multiplying it by a float. And look at this, I declared a float earlier. It's almost like I knew where I was going with this. So I'm just gonna say my velocity is equal to that direction times my move speed. I figured out what direction I need to move in, and let's just scale it up to match whatever my speed is. So let's run that. And now he's moving a bit faster, giving it a good chase. Sweet, and now you can try to avoid this guy, but if you hit him, you die, you go to your spawn point. Sweet, okay. That is my 3 core examples for understanding vectors. First, we simply declare a vector and use it to set a position. Pretty simple. Then we use a vector to describe some motion and apply that motion every frame. And finally, we do some math here to find a direction using vectors and then use that direction to move a ghost. This is a classic chasing the player structure. Vectors show up everywhere. And if your game involves movement, which almost all of them do, you're going to want to get good at vectors. I highly recommend if you're in a place where you could take a physics class or Algebra 2 or pre-calc math class and learn more about vectors in that math space. It is super helpful because they show up everywhere. A great next step from here is to practice. You need to try using vectors in different applications and try to wrap your head around them. My recommendation to you may have noticed I did not go over how to make the player move in this. That is a great practice problem. Look up a guide on how to do player movement, and as you work through it, think about the vector math that's happening. Think about how those vectors are describing our player's position and their motion over time. Thank you for watching that video. If that was helpful to you and you want to see some of this stuff in action, go check out the demo for our game, Cappy and Tappy. It just released on Steam. We've got a bunch of new stuff in there, and we've got a new endless mode. We've got a new boss fight that I'm really excited about. A lot of cool stuff to check out. So we really appreciate if this was helpful to you. Go do us a favor and wishlist that on Steam and go try it out. Let us know if you like it. Thanks.